Hello, am I audible?
Yes, ma'am.
Okay. So today is your first revision session. So in this session, we will talk about sequences and limit continuity of functions. Okay. So let's wait for 5 more minutes and then we'll start our session. Meanwhile, if you have any doubt, you can ask.
Ma'am, I have doubt in Big Four practice assignment question number 8. I don't know how to approach this question.
Okay. Yeah, just 1 minute. Question number 8 now.
Yes, ma'am. All three question I didn't solve, but if you explain how to solve it, I will solve all of them.
Okay, so here's some information is given for 8, 9, 10, right? This one, right? An electrical engineer is designing a signal processing circuit that amplifies weak audio signal. The circuit input voltage denoted by V. It passes through an amplifier with gain function G of V. So here one function is given to you and that function takes the input to be V. So the engineer needs to ensure that the amplifier is operating within its range uh, for accurate signal processing. Okay, so the amplifier is gain function continuous. So here simply you have to check the continuity of this function. Okay, so here the function is given to be, so this is question number 8, practice assignment 4. So here g of v is given to you to be 30 minus of some polynomial is here, 5, 40, 20, 5v square plus 40v plus 20, something like that, and then under the root of v plus 1 the whole square minus v
Whole
plus 2
square
to the
नहीं मैम,
power
power
14.
4 है.
Okay, okay. v
V
plus
plus to the power 4.
4 to the power 4 minus 16 is given,
2 to
right?
the power 4, ma'am.
Acha, v
V
plus
plus
2 to
2
the
to
power
the...
4 है.
Yes, ma'am.
Mm-hmm. Okay, so v plus 2 to the power 4. So here this function is also some combination of linear function and rational function, right? So ये जो function है, this is a constant function, right? So constant function is always continuous, so we don't have to bother about this term. Now the only thing we have to check that is this function is continuous or not. Okay, so this is a question. The question is that is this continuous or not? So as we already seen that if we have a function f of x, which is written in the form of p of x upon q of x, where if both px and qx are polynomial, if both are polynomials, then fx will be continuous, at x is equals to x naught, if and only if q of x naught is not equals to 0. Right? So we know that if we have such kind of rational function, this is the result for rational function, right? And we already seen why this holds, right? So if we have a rational function in the form of p by q, where p and q both are polynomials, then we know that this function will be continuous at all those points where our denominator is not vanishing, right? That means qx is not becoming 0. Now here you observe that it is not the denominator is not a polynomial, right? So here denominator is something under the root of v plus 2 the whole to the power 4 minus 16 is given to us. But what we can do, we can simplify this equation, right? And we know that first of all, try to figure out when will this either it will be equal to 0, or we know that under the root is not well defined when we have negative here, right? Negative quantity here. So but since the power is 4, so this won't be negative at any v. I think it will be negative, but let's see. So here we have to check that this g is the amplifier gain function is continuous or not. Okay, so we need to check the continuity of this function. Now we know that here this function will not be continuous if we obtain some point where our denominator becomes 0. And we know that this can be equal to 0 when we put v is equals to 4, right? So if you put v is equals to 2, not 2 because 4 is there. So okay, so simply put v is equals to 0. Okay, so this is the denominator. So here if I put if you put v is equals to 0, then this will become under the root of 2 plus 2 to the power 4, 2 to the power 4 minus 16, which is equal to 0. So that means that v is equals to 0, denominator becoming 0, but the numerator is not becoming 0, right? So p of 0 is not equals to 0, but q of 0 is equals to 0, right? Q of 0 is equals to 0. So that means we have one point at which our denominator is becoming 0. So that means this function is not continuous, at v is equals to 0, right? So the answer will be no. So that's how you have to check for continuity of any rational function. Okay, so here you have to use that particular method. Is that fine?
Yes, ma'am.
You got the approach, right? Whenever we have rational function, how we do? We just look for a point which make our denominator to be equal to 0. And here that point is v is equals to 0. Okay.
Okay, ma'am.
Okay, so now let's start for revision of week 3 and week 4. So I'll go. Yes, Amisha. Yes.
Ma'am, I want to know that only that it is a revision session or like normal session only. But
No,
now
it
what
is a
will
revision session for week 3 and 4. So I'll cover the main topics from week 3 and 4, and then we'll try to solve some of the
when will
questions, 2-3 questions. Sorry?
and ma'am, one thing I want to know that
Hmm.
means any link is there of a revision session one like week 1 and week 2?
Yeah, I think week 1, week 2 revision session will be on Friday. This
Okay,
Friday.
so that will be on
Yeah.
Friday. Yeah, on
That
25th.
will be on Friday. 25th.
Okay, ma'am.
Actually, that's supposed to be today, but sir got busy, so I'm
Yeah.
taking now. Okay.
Okay, ma'am. Thank you.
Okay, so now let's start week 3 portion first. So in week 3, we talk about sequences and what is the limit of a particular sequence. Okay, so I'll start with the limit definition itself, because I think you guys are familiar with sequence. What is a sequence? So let's start with the definition of sequence. So what is a sequence? So sequence is nothing but a function from natural number to the set of real number. This is known to be a sequence for us. And there are 2 to 3 ways to represent a sequence. First is just listing out the element of a sequence. So suppose I have a sequence which has elements. I mean, the list will be 1, 2, 3, 4, and so on, right? So this is one way of representing a sequence. Another way, by giving the expression for an n term, expression for nth term. That means if you list out your sequence, then this will be your first term. We denote it by A1. This will be your second term, A2, A3, and so on. So in this way, whatever term comes at the nth place, this will be n. In this case, this is your nth term, right? So another way is by giving an expression for nth term of a sequence, we can express a sequence, right? So in this case, our an will be equal to n, right? And the third one is the recursion relation. That means if you give some relation between an and an plus 1, or an and an plus 1, or an plus 2, such kind of relation is known to be recursion relation. Why it known to be recursion relation? Because it is using the previous terms to judge or to calculate the next term. Okay, so that's why it's known to be a recursion form for a sequence. So in this case, our recursion will given as a1 is equals to 1, and our an plus 1 is nothing but an plus 1. That means we are adding 1 in every term. That's why it will be 1. 1 plus 1 will be 2. 2 plus 1 will be 3, and so on, right? So these are the 3 forms for expressing any sequence. Now, there is one... there are 4 type of sequence we want to know: bounded, unbounded, and monotonically increasing, monotonically decreasing sequence. So let's start with bounded sequences. Okay, so suppose a sequence is given to you. In general, whenever we see sequence, we write it in this way: an with curly brackets. So this symbol means a sequence, and its nth term is given by an. So we say that now in bounded sequence, there are 2 type of bound. One is known to be upper bound, and the another one is known to be a lower bound. So when we say that a sequence is upper bounded, if we are able to find out a real number capital M in such a way, so if there exists, this is a sign for there exist. If there exists and capital M belongs to real number in such a way that all the term of the sequence is actually less than or equal to this capital M, then this sequence is known to be bounded upper, and this this capital M is known to be one of the upper bound of a sequence. Okay. Now why I'm saying one of the upper bound, because if M is the upper bound, then you can simply just that M plus 1 will be the upper bound, M plus 2 will be the upper bound. That's why I'm saying one of the upper bound, right? So if there exists one real number which can bound the term of a sequence, for example, if you plot your sequence over the real line, suppose this is your real line, and if you plot a sequence means if you denote the natural number here, that means 1, 2, and so on, 1, 2, 3, and so on, and you denote the term of a sequence over y-axis. Suppose this is your sequence. Let me draw it here. Okay, so suppose these are to be 1, 2, 3, 4, 5, and so on, and these are the term of a sequence. That means a1, a2, a3, a4, and so on, right? So by bounded above means you should be able to find out one value capital M in such a way that your term of sequence does not able to, they are not able to cross this line, not able to cross, right? That simply means that an is less than equal to capital M for all n, right? So such type of sequence are known to be bounded above. Now similarly, we can define bounded below. Bounded below means you should be able to find a small m in such a way that all the sequence of that means all the term of a sequence should be greater than or equal to the small m. That means if there exists and small m belongs to a real number in such a way that an is greater than or equal to the small m, then that particular sequence is known to be lower bounded, and this small m will be one of the lower bound. Okay. Now when we say our sequence is bounded, so if a sequence is bounded above as well as bounded below, then that sequence is known to be bounded sequence. Okay. So what is the bounded sequence? So bounded sequence means if an is bounded above, Bounded above means there exists an upper bound. If an is bounded above as well as bounded below, then the sequence an is a bounded sequence. Then an is a bounded sequence. Okay, now I'll just take some simple examples. Let's try to judge them. So suppose if you have a sequence, for example, suppose you have a sequence an is given to be 3n plus 2 upon 3n plus 7. Right? Suppose this is a sequence. This is for all n belongs to natural number. Then is this bounded above? Yes or no? True or false? And is this sequence bounded below? This take 2 to 3 minutes. 2 minutes I'll give you an answer. What do you guys think about this sequence?
This is bounded below sequence, ma'am.
Okay, bounded below by which? By what? Can you give me
When we put
one?
when we put n equal to 0, it's become 2 by 7. This is its
Okay.
lowest value. And when we put n equal to infinity, it's goes to approaches to infinity.
No. You're not correct here. Just observe this sequence. This sequence is not something. It's not that 1 by n type of sequence, right? The sequence has a different formula. It is 3n plus 2 upon 3n plus 7. So just observe the term. You can guess the upper bound and lower bound of the sequence. That's why I say just take 2
I think
minutes and try to figure it out.
both are 0, ma'am. Upper bound and below one both are 0.
It is upper
0
bounded.
and 1, ma'am. 0 and 1.
Okay,
It's
Ritu,
both.
your answer might be correct, but just give some others to time, okay, to think.
Ma'am, it is upper bounded.
Okay, upper bounded by?
1.
Okay, good. And what about lower bound?
0. 2 by 7.
0. Okay, lower bound is 2 by 7. Yeah, so it is correct that this sequence is a bounded sequence, indeed, obviously. You can just judge this by observing, right? So here an is given by, so this is a solution. So here your an is given as 3n plus 2 upon 3n plus 7. So we know that if we take any natural number, so if I take any n belongs to natural number, then obviously 3n plus 2 will be less than 3n plus 7, right? Because this is what? This is 3n plus 2 plus 5. So that means I am adding something in my original quantity, right? So that's why it's greater than 3n plus 7. So that means it is obvious that 3n plus 2 upon 3n plus 7 is strictly less than 1, correct? So that means the upper bound will be 1. So it is bounded up. Right. Now, what about lower bound? So here it is quite obvious if we take any n belongs to natural number, then this quantity 3n plus 2 will be always greater than equal to 0, and 3n plus 7 is also greater than equal to 0. So in general, you can say that your an is greater than equal to 0, and the 0 is the lower bound. Or else you can precisely also say that 2 by 7 is the lower bound. But yeah, this is a overall picture. I mean, by just observing the sequence, you can tell that, okay, 1 is the upper bound and 0 is the lower bound. So that's why the sequence is a bounded sequence. So it is a bounded sequence. Okay. Is there any confusion in bounded sequence? Yeah.
Ma'am, is it we have said that the upper bound is 1. the upper bound can be less than 1 also, right?
Yeah, it can be less than 1. If
So
you
then
compute precisely, I think this sequence will be decreasing sequence, maybe.
Yes, ma'am.
Right, because denominator is bigger than the numerator. So as you goes to infinity, this will be a decreasing sequence. It converges to 1, I think. So yeah, the lower one could be less than 1, but yeah, that's correct. So what's your doubt? That's only right.
So is that okay? I'm just trying to understand.
That will be okay. If you find any number which is also less than 1 and all n are less than equal to that also your upper bound.
No, that is fine. I'm saying that when we say that upper bound is 1, knowing the fact that it can be lower than 1, is that fine? I'm asking.
Yeah, that will be fine. Because that's why I say there is not one particular upper bound.
Okay, thank you.
Right. Okay, anything else about bounded sequences? Let's go to monotone sequence now. Okay, so now we know that if we have a sequence an, then this sequence is called increasing. Increasing if an plus 1 is greater than equal to an, right, for all n. Right, and similarly we call the sequence to be a decreasing sequence if an is greater than equal to an plus 1 for all n. Right, so these are two known to be monotone sequences. Monotone behavior means either increasing or decreasing. Sometimes increasing sequence also known to be non-decreasing. So that's up to you what terminology you want to use. And sometimes non-decreasing sequence is also known to be non-increasing. Okay, so these two names are there. Now let's go to limit of a sequence. So what do we understand by limit of a sequence?
Ma'am, I have a doubt.
Yeah.
What is the meaning of base and inductive in the monotonic?
What is the meaning of what?
What is the meaning of base and inductive in monotonicity?
Base and inductive means? I'm not getting. In monotonicity, we just define two things, na? Increasing, decreasing. What do you mean by base and inductive behavior?
Okay, ma'am, not a problem.
Okay. So now what is the limit of sequence? So limit of sequence actually tell us that if our n approaches to infinity, then where will our terms of sequence an approaches, right? So we are actually want to find out that particular number. If that particular number exists, then what will be that number where our term of sequence will approach? That's the basic question for limit. Now, if you graphically understand this, so graphically it means that if you plot your term of sequences, so suppose these are natural number, these are your term of sequences, then there should exist some particular number L in such a way that if you draw a little rectangle over here, then infinitely many term of your sequence should lie in between this particular rectangle. This is known to be limit of sequence. So mathematically, it has a very abstract definition. So we say that limit n goes to infinity, an is equals to L if for all epsilon strictly greater than 0. Again, epsilon is nothing but a positive number, a small positive number. Okay, so if for all epsilon greater than 0, there exist and capital N epsilon belongs to a natural number. So ultimately, we want to find out a stage. So this is your stage N epsilon in such a way that it is possible that some of the terms which are lying before this N epsilon are out of this particular rectangle strip. But after this N epsilon, all terms of the sequence should lie in between this particular rectangle strip. Okay, so that's why this is known to be N epsilon. And why it is epsilon? Because it is depend on your choice of epsilon. Okay, so we say that limit n goes to infinity, n is equals to L if for all epsilon greater than 0, there exists an epsilon belong to a natural number in such a way that that all term of the sequence, that means all an, should lie between this particular rectangle strip, and this strip is nothing but L minus epsilon, L plus epsilon. Right? So an should lies between L minus epsilon and L plus epsilon for all n greater than equal to this particular n epsilon. Okay, then we say that our sequence will have a limit, and that limit is nothing but this particular capital. Okay, is that fine? Any doubt in limit of sequence definition? Anything you want to clarify? Some term is not that helpful or something?
Ma'am, please repeat one time more.
Okay. So here what we want to understand, that if n goes to infinity, where does our term of sequence an reaches, right? We say that this limit is equals to L, is equals to this particular number L. If we take any small rectangular strip over this L, right, any small. So for this any small, I am taking this epsilon greater than 0. This epsilon greater than 0 will give us a freedom that you can choose a very narrow rectangle strip here near the L. Okay, so we say that this particular number L will be our limit if for all epsilon strictly greater than 0, there should exist a stage n epsilon, after which after which all of the term of a sequence should lie between this particular rectangle strip, and that's is denoted by the sentence. This sentence will refer to the scenario that after this n epsilon, all of the sequential term will lies between this particular rectangle strip, L minus epsilon and L plus epsilon. That's the meaning that there exists n epsilon belongs to a natural number in such a way that an is lying between L minus epsilon and L plus epsilon for all n greater than equal to n epsilon. Okay, that's the definition of limit of a sequence. Okay. Now let's yeah.
May I ask you to do this a little with some actual numbers?
Okay.
And plot it on the graph. So if
Okay.
everybody else is all right with it, because it might take some time. Because I'm getting
Okay.
it partially, but I'm still not very comfortable in absorbing it.
This regular definition. Solving the limit of sequence.
No, to understand, this epsilon and the limit.
Okay.
I understand the limit, but I'm still not able to. That epsilon idea is still very abstract for me.
Yeah, this epsilon might be a little bit hard to digest, but yeah, you have to spend some time. So we can do this activity at the end. I think no one has a problem at that.
Okay, fine.
Okay.
Ma'am, one thing, this
Yeah.
epsilon is you are referring to error, right? Like
Not an error type of thing. It just gives us a freedom that we can choose a very narrow strip around M.
suppose
That's it.
my function is converging to 0.5. Okay. Then I can choose between suppose 0.6 or 0.4, correct?
You can choose between 5. You can choose between 0.6, 0.4. Also, you can choose very narrow. I mean, you can choose 0.5 is the limit, right? So you can choose
Yes.
0.499999, and similarly 0.5111. So that's also your epsilon. So this epsilon just gives us a freedom that we can choose a very, very narrow strip.
Yeah, we can roam around that particular circle. Means
Right.
some extra points, correct? Okay. Okay then.
Ma'am, just 1 second.
Yeah.
Can you just give one example of an application or a use case for this?
The limit is the use. I mean, we calculate the limit of function 1 by n using this definition, right? I mean, if you want to find out this, we already know that the limit n goes to infinity of 1 by n is equals to 0, right? Now, if you want to justify this using this particular definition, then what you can do? Okay, so suppose epsilon is strictly greater than 0, be any positive number, right? Okay, then what is my what I have to do? I have to find out n epsilon in such a way that then I want to find n epsilon in such a way that this thing should happen, that this particular 0 minus epsilon is less than or equal to 1 by n less than or equal to epsilon for all n greater than or equal to n epsilon. Right. Now here what we do, we just choose our n epsilon wisely. that if epsilon strictly greater than 0 is there, then we can choose n epsilon in such a way that this condition should hold. Now here you observe that I want 1 by n less than equal to epsilon, right? So that means 1 by epsilon is greater than equal to n. Right here? Huh. So now what n epsilon I can choose for saying that this will be my case. That will be my case. So I can choose n epsilon to be, if I choose 1 by epsilon, then n epsilon, okay. Okay, fine. Sorry. So that means if let's say I choose, so let's choose n epsilon to be equal to 1 by epsilon. 1 by epsilon. Then if, okay, so let's choose n epsilon is equals to 1 by epsilon. Then if n is greater than equal to n epsilon, that means n is greater than equal to 1 by epsilon, which will implies 1 by n will be less than equal to epsilon. Okay, and it is automatically greater than equal to minus epsilon, because epsilon is positive quantity, 1 by n will be always greater than equal to 0. So it will lies between this term. So that means for every epsilon, my n epsilon is nothing but 1 by epsilon. Okay, so this is a given quantity to us, and this is the thing we have to find. We have to find if I want to say that 0 is my limit. So for every epsilon, I am able to find out one n epsilon for which this condition holds. Okay, so here you can choose epsilon to be 0.5. Let's choose 0.5. Then what will be your n epsilon? 1 upon 0.5, right? That will be 2, correct? So here for all n greater than equal to 2, I have this condition that minus 0.5 is less than equal to 1 by n less than equal to 0.5. So that's the one example you can thought. But although it's very hard to judge a limit via this method. Okay, is that fine?
Yeah, thank you.
Now we classify our sequence based on their limits. So I think you guys know what is the convergent sequence. So we say a sequence is convergent if there exists a limit L which is finite. Then we say that our sequence is convergent. For example, 1 by n. 1 by n is a convergent sequence because 1 by n converges to 0 and 0 is a finite number. We say that our sequence diverges to infinity if this limit, that limit n goes to infinity, an is equals to infinity. Or simply you can say that as n goes to infinity, an is also going toward infinity. Then we say that our sequences diverges to infinity. And we say that our sequences diverges to minus infinity. If n goes to infinity, will imply an goes to minus infinity. It simply diverges to minus infinity. And if none of the scenarios happen, then we say that there does not exist any limit. Does not exist any limit. Okay, so this is the type of sequence or classification of sequence you can see. Now we have some rules to compute the limit of a sequence. I think they are very basic, simple rules. That means if we have limit n goes to infinity, an is equals to a, limit n goes to infinity, bn is equals to b, then any constant multiplication of this sequence will goes to constant multiplication of their limit. That means limit n goes to infinity, Can is nothing but Ci. And limit n goes to infinity of their summation or subtraction, whatever you'll take, is simply a plus b. Okay, but here assume that first this thing is happening. Okay, if this is not happening, we cannot conclude that. Okay. I also did one question regarding this, that in the previous session, I think I told you that if f plus g is continuous, then it is not always the case that f and g both are continuous. So same thing happen here also. So it is not always true that if an plus bn converges to something, it does not imply that an and bn both are convergent sequence. A and bn both are. It does not imply that an and bn both are convergent sequence. And I'll encourage you to find out one example for this. It's an exercise. Okay. So this same thing happened. So that's why this rule first assume that this is your first assume. And then this is your result. So if you don't assume that A and Bn are convergent sequence, then these results may not hold always. Okay. The third point is the multiplication, that limit n goes to infinity, an, bn. Can you guys suggest one example for this scenario, that if an plus bn is converging, it is an plus bn is convergent, but an and bn both are not convergent sequence. Can you
Then
guys
an is
give
equals
us an
to
example?
an is equals to n and bn is equals to 1 by n.
An is equals to, but summation is there. Bn is equals to 1 by n. Yeah, that won't work, no? Convergent means finite limit I want. Okay, just think about it. So that now here also, if bn is not equals to 0 and b is not equals to 0, then limit n goes to infinity, an by b here, simply a by 2. Anyone? An example? It's very easy. Just take 1 minus 1 sequence. That sequence is not convergent, and if you add them, then their summation will be convergent. Okay, so what I mean, so it's a solution. So suppose if you take an to be equals to 1 comma minus 1 comma 1 comma minus 1 comma and so on, and simply take bn to be just opposite sign, minus 1 1 minus 1 1 and so on. Here if you make an plus bn, then an plus bn is nothing but 0, right? Constant sequence. And an plus bn, so this will implies an plus bn converges, but both an and bn are not converging, or does not converge, they do not converge, whatever you have to write. Okay, is that fine?
Yes, ma'am.
Okay. Now similarly you can think about that, what if an minus bn converge, an minus bn will be same as this, right? What if an bn converges, then what can you say about an and bn, right? So these are the interesting questions. Okay, now let's try to solve some of the examples, and then we'll go to limit and continuity of a sequence. Okay, and now first of that, what is monotone convergence theorem, right? MCT I have to. Okay, so what is monotone convergence theorem, MCT? So monotone convergence theorem actually uses two property of a sequence to say that a particular sequence converges or not. Okay, so the first thing is, the first statement says that if a sequence is non-decreasing, non-decreasing means increasing sequence. So if a sequence is non-decreasing plus it is bounded above, then it will imply then it has a limit. That is what monotone convergence theorem says. That if a sequence is non-decreasing plus it is bounded above, then it has a limit. And the second statement says this reciprocal or something like that, right? If a sequence is non-increasing or decreasing plus bounded below, then it will imply that then it has a limit. Okay, so this is known to be monotone convergence theorem. Now we can use this theorem to say that if a sequence has something like this form, suppose in previous question I have taken an is equals to 3n plus 2 upon 3n plus 7, right? We know that the sequence is bounded above and bounded below. And here one thing we know that since if you consider an is nothing but 3n plus 2 upon 3n plus 7. Now what will be an plus 1? So an plus 1 is nothing but 3 times n plus 1 plus 2 upon 3 times n plus 1 plus 7, which is nothing but 3n plus 5, right? Because 3 plus 2 will be 5, and here 3n plus 10. Okay, so we can actually compare that. Okay, here as n goes to infinity, the sequence is kind of decreasing sequence, or else this is not convincing for you. What we can do, we can just take common n, and then it will be much easier to feel that it is in a decreasing sequence, right? So if you take n common from the numerator denominator and cancel it, what we will get? We will get 3 plus 2 by n upon 3 plus 7 by n. Right? And we know that 1 by n will have a decreasing kind of nature. So an will be a decreasing sequence, plus it is bounded below. So that's why it will be a convergent sequence. It will imply an is a convergent sequence. Right. So the main application of monotone convergence theorem occur when you have a sequence which is given in the recursion form, right? Because there this increasing nature or decreasing nature is very easy to judge, and bounded above and bounded below also you can easily judge. For example, if you have a sequence given by geometric progression or arithmetic progression, there also you can use this to find out that sequence is convergent sequence. Any doubt in MCT, monotone convergence theorem?
No, ma'am.
No? Okay, so let's now try to do some of the examples. So I'll just take two examples or one example. So suppose an is given to be 10 minus n, 11 plus n, 12 plus n, 9 minus n. Okay, this is your an. And upon we have 11 plus n, 12 plus n, 13 plus n, 14 plus n. Then does an converge? And if yes, then what will be the limit? Please answer in the chat box. That will be helpful so that others can think about it. Okay. Try to solve it. I'll give you 3 minutes.
Ma'am, its limit is 1.
Okay. So it will be convergent, right? Because limit is
Yes, ma'am.
exist and finite. What about others? They also think that it's 1. So yeah, correct. It is a convergent sequence and the limit is 1. And how you tackle this such kind of question is simply, since again we have a rational function, so numerator denominator is there, just take all the n common, and then the sequence will reduce in the form of 1 by n, and we know that 1 by n goes to 0 as n goes to infinity, right? So we use the same thing. So solution will be, so since an is equals to, this will be 10 by n minus 1, 11 by n plus 1, 12 by n plus 1, and 9 by n minus 1. Right. And in the denominator, I have 11 by n plus 1. And here I'll get n to the power 4, but in the denominator also I'll get n to the power 4. So both of the things will get cancelled. And here it will be 12 by n plus 1 and 13 by n plus 1, 14 by n plus 1. Right. And we know that this the sequence goes to 0, this goes to 0, this goes to 0, this goes to 0. And same thing happen in the denominator also. So at the end, the limit n goes to infinity an is nothing but minus 1 into 1 into 1 into minus 1 upon all our 1s here. So which is equals to plus 1. So yes, the sequence is convergent and the answer is, the limit is plus 1. Okay. So I think it's easy one. Now let's go to continuity and limit of a function. So limit is actually defined by using the limit of a sequence. So if you understand what is the limit of a sequence, then continuity or limit of a function is nothing but just same kind of thing, right? So here I'm skipping one topic, which is the function of the form a to the power x and x to the power x. So I think we have already covered that in the last session. So I'll suggest you, if you have any doubt on that particular topic, you can ask, or else we'll jump up to continuity of function. Any doubt over that particular topic, a to the power x and a to x to the power a functions? Yeah. Any doubt?
If you can quickly revise it once, it'll be nice.
Yeah. Sorry. So actually, our aim is to find out that what will be the value of a to the power x when we take a to be x to be a real number and a to be real. That's the main thing we want to judge. So we know that if I have a fixed real number a, and if I take any natural power, then it's nothing but the multiplication of all a's n times, right? Similarly, if I have a to belong to the if n belong to the integer, so here n belong to natural number, here n belong to integer, then we can actually decompose into a something like this m into a to the power minus k type, right? Because there m will be positive and k will be a negative thing. So ultimately, what is the meaning? That if n belong to integer also, there also we have a sense that a is nothing but some a to the power r upon a to the power s type of thing, where your both r and s are positive numbers, correct? So we can define a to the power n for natural number and integer also. Now what about when a to the power p by q appears, where p by q are integers? So that means a to the power rational appears. So this thing is also can be converted into a to the power 1 by q into a to the power p, or sorry, to the power p. Okay. So now here what has become, this thing is well defined to us because it is some number to the power integer, or some number to the power integer. So that is well defined for us. Now what happen if I have a real number to the power rational? So as we see that we have a sequence which converges to root 2, similarly we can find a sequence in such a way which converges to a to the power 1 by q also. So that means such type of number we can define by a limit of a sequence. So e to the power q can be defined as limit n goes to infinity of some sequence un. And that particular sequence you can judge by whatever sequence is given to us for root 2. Say similar type of sequence work for 1 by q also. Okay. And similarly way we can define a to the power r for any r to be irrational number, right? So the ultimate what you can say ultimate outcome of this particular discussion is that a to the power x is well defined for all x belongs to real number and a belongs to real number. So thus, using this particular information, I can define a function from real number to real number, which actually send every real number to a to the power x. First I'll fix x, and then I define this type of function, and that function is known to be exponential function. And similar kind of function is if you take any real number goes to real number function, again let's name it to be g, that in this function x is going to x to the power a, right? So here I am taking x to the power, I mean a to the power x, in the below I am taking x to the power a. Okay, so these two functions are very helpful and it occurs many times in your calculus. You will find such type of function everywhere. Okay, so that's the motive. And in the lecture, I think we discuss about the graph of such type of function. So yeah, you can play with the graph also. Okay. Now let's go to limit of a function. Okay, so again we say that limit extending to x naught f of x is equals to L if for every sequence an which is converging to x naught, this f of an sequence should converges to x. So this is the definition of limit. So limit means, so we say that if x naught going to x, x is going to x naught, we say that f of x goes to L. This means that if x goes to x naught, then f of x goes to L. If for every sequence which converging to x naught, if you compute the functional sequence there, that means just apply f on a and you will get a sequence. So that particular sequence should converge to L. This is the meaning of limit of a function. Okay, is that fine? Any doubt here? It's a very simple definition. You will take for any sequence, this scenario should happen. So if this is happening, we say that L is the limit. Okay. Now let's try to figure out the limit of two particular functions. So if we have a constant function f of x is equals to c, then we know that the limit of x goes to x naught for any x naught belong to a real number, f of x is nothing but c, right? Because as x goes to x naught, fx will always goes to c because it is just a constant function, right? And similarly, if we have another function f of x is equals to x, the identity function, then we know that limit x going to x naught, f of x is nothing but x naught, because as x goes to x naught means f of x will also goes to x naught because f of x is nothing but x itself. Okay. Is there any doubt in limit of a function or these two things? Because these two are base limit. If you understand these two, then you can compute the limit of rational polynomial and so on. Hello.
Yes, ma'am. Yes.
Okay, fine now. Am I moving too fast? You can also say it. Okay. Now let's try to figure out some rules of limit of a function. And what is continuity? So continuity is nothing. So we say f is continuous at x naught if limit x going to x naught f of x is equals to same the value of function f of x naught. Then we say it is continuous at x naught. So continuity is nothing but again a particular type of limit, you can say, right? Now let's try to break down two things. First is left hand limit and right hand limit. Left hand limit and right hand limit. So what is left hand limit and right hand limit sequentially? So sequentially means, so suppose this is a point x naught. So if we consider any sequence which converges to x naught from its left hand side, that means this is the sequence. Suppose this is a1, a2, a3, a4. Okay, so if I take any sequence which is converging to x naught from its left hand side, then what will be the convergence of this particular sequence f of a? That particular thing is known to be the left hand limit. What I mean by that, so we say same thing, that limit x going to x naught minus. So the left hand limit is denoted by this particular minus. This minus means we are approaching x naught from its left hand side. So limit x going to x naught minus f of x is equals to L if for all sequences an such a way that an is less than equal to x naught, because then only an will lie over the left hand side of x naught, right? In such a way that an is less than equal to x naught and an converging to x naught should imply that f of an converges to L. This is the formal definition. If you don't understand, that's also fine. So ultimatum, you have to understand if we approach x naught from the left hand side, where does our function goes? That's the main meaning of left hand limit. Now similar thing with right hand limits. What is right hand limit? So if you approach our point x naught from the right hand side, then where our function approaches, that's the meaning of the right hand limit, right? So left hand limit and right hand limit are easy to understand when we see over some graph. Okay, so let's take one example here. This is the example. So suppose this is our graph, and you guys know the rule, right? If we have a hollow point, then the function value is not there, and in place of that, if I have a solid point, then the function value is there. So suppose this is my graph of a function down here. This is your y-axis, this is your x-axis, this is your function f. And suppose this point is x is equals to 2, this is x is equals to 4. And this particular point is 2 comma minus 5, let's take, and this is 4 comma 1. Okay, then I'll ask you some questions. So here, by observation of graph, I think you can say, so what is the left hand limit of a function f at x is equals to 2? What will be the value?
-5.
-5, correct? Everyone agree with this? Why it is -5? Since we are approaching x is equals to 2 from the left hand side. So if I approach from left hand side, I will follow this path. My function will follow this path, right? So as x goes to, as we are approaching x is equals to 2 from the left hand side, the function value will approaching toward -5. Correct, -5. You're right. I should give over here one name. It is x, let's take it to be -2. That's fine. So that means as I approach, now here the main thing is you are approaching toward x is equals to 2 does not imply that you should take the left hand limit to be equal to -2, because function is getting more closer and closer to -5, not -2. Okay, so here as you approaches x is equals to 2, my function is actually getting much closer and closer to the point y is equals to -5, not y is equals to -2. So that's why the left hand limit of f at x is equals to 2 is nothing but -5. Okay. Now what will be the right hand limit of f at x is equals to 2? What will be your answer? You have to find out that point where function is getting closer and closer. -2, correct? Because function is approaching from, we are approaching from right hand side, and as we approach from right hand side, the value of function is getting much closer and closer to y is equals to -2, correct? So that's why the right hand limit of function at x is equals to 2 is nothing but -2. And similarly, what will be the left hand limit of a function f at x is equals to 4? Now you guys will answer in the chat box. Okay, don't answer verbally. Answer in the chat box. I have to see how many answers are there. Okay. So what will be the left hand limit of f at x is equals to 4? It's a left hand limit, not right hand limit. Left hand limit at x is equals to 4.
It's 1, ma'am.
Left hand limit,
I think -2, ma'am.
-5.
-5.
Left hand
-2, I
limit.
think.
Okay, so what's the difficulty here? See, we have to approach x is equals to 4 from left hand side. So this is x is equals to 4. This is its left hand side. So as you approach x is equals to 4 from left hand side, where does your function goes? So it actually goes toward y is equals to 1, because this is the nature of function, right? So as we approach x is equals to 4 from left hand side, as we go from here, the value of function will follow this path, this particular constant line, y is equals to 1, -2, correct? So that's why, so that means as we go much closer and closer to x is equals to 4 from the left hand side, the value of function will get much closer and closer to -2, not 1, right? Because 1 is approaching from the right hand side, not from left hand side. Okay. So that's why the left hand limit of x is equals to 4 is nothing but -2. Is there any doubt in this question? 3 points are clear to you guys? Any confusion? See, what you have to do, you have to observe where does your graph is going. What is the point at which your graph is getting much closer and closer? Okay. It's not that that the particular value of function should be there. In case of limit, we don't bother about the value of function at that particular point. Only when we want to talk about the continuity, we need the value of function at that point. But if we want to talk about limit, we just know that what will be that point where my function is getting much closer and closer. Okay. So here in this case, at x is equals to 4, we are getting much closer and closer to -2, right? Because function is following this path. So as x goes to 4, this goes to y is equals to -2. So that's why the limit is -2. Okay. Now let's try to understand this phenomena by one small example. So suppose this is the graph of your function. So this is hollow point at only 0. Okay, I make it, this is 1. So suppose a function is given by this particular f, then if I ask you one question, so first question A will be the limit x going to 0, f of x is equals to, what will be the limit? And the B will be, is f is f continuous at x is equals to 0. Okay, what will be your answer? Sorry.
When the limit tends to 0, it's 1, ma'am. Its value become 1 and it is not continuous function.
Correct. Everyone is agree with his answer, right? So see, as how could you tackle about limit thing? So here you observe. So one result is there. I think I haven't stated it. So if the left hand limit is equals to right hand limit, then we say that the limit is will be that particular value. And if the left hand limit is equals to right hand limit to the equal to the function, that's what I mean. So if left hand limit of f at x is equals to x naught is equals to right hand limit of f at x is equals to x naught. This will imply that limit x going to x naught f of x exist, and it is equal to this quantity, whatever quantity is here. Left hand limit is equals to right hand. Okay, and the second thing is, if left hand limit of f at x is equals to x naught is same as the right hand limit of f at x is equals to x naught is same as f of x naught. If this particular equality holds, then we say that f is continuous. Is continuous at x is equals to x naught. It holds vice versa. So that means if f is not continuous at x is equals to x naught, one of these quantities are not equal to each other. Okay, so this is one thing. And obviously we are considering them to be finite, not the infinity case. Okay. So here what is happening? So here if you compute the left hand limit of f at x is equals to 0, what will be the value? So here left hand limit of f at x is equals to 0 is nothing but 0, because as we are approaching 0 from the left hand side, the function is also approaching 0 from via this particular line, y is equals to minus x. Okay, and the right hand limit of f at x is equals to 0 is again 0, because again we are approaching 0 from the right hand side, then the function is actually following this particular path and it is also approaching towards 0 from the right hand side. So that's why the right hand limit of f at x is equals to 0 is 0. So that's why the limit x goes to 0, f of x is equals to 0. But here at 0, it's a hollow point. So we know that whenever we have hollow point, the function value is not there. The function value will be at the solid point. So here the solid point is at equal to 1. So that means the value of function at 0 is nothing but 1. So that's why we are getting that limit x going to 0, f of x is equals to 0, which is not equal to f of 1, which is equal to 1. So that's why this function is not continuous at x is equals to 0. Is that fine? Any doubt in this function or this question?
No, ma'am.
No, fine. Okay. Now let's try to solve some of the question similar type of thing. Any doubt in continuity, limit, left hand limit, right hand limit? Something is not clear to you? Anything? Okay, fine. Now let's talk about a limit of some power functions. So I think this is little easy. So limit x goes to 0 of x to the power 4. What will be the limit here? What will be the answer?
0.
It's too easy, right? Because it's a polynomial, right? So it's a polynomial and we know the result that limit x going to x naught, p of x. If p of x is a polynomial, then it's same as p of x naught, right? So you can use this result to compute it. Now, in case of that, if I have a rational function, something like this, limit x going to 0 of x to the power 100 or 110 plus 10 x to the power 99 minus 1 upon x plus 1. Then what will be your answer? What will be the limit here?
0.
Sure, 0?
No, ma'am. -1.
The limit will be -1, correct? Because it is an example of rational function. So this is one result, that if we have a polynomial, so then the limit x goes to x naught, p of x is equals to p of x naught. And the reason behind that, you can go in the lecture and check why this is happening. Okay, it's a very easy, because polynomial is nothing but a combination of linear function and constant function. And both functions are continuous. So that's why polynomial is also continuous. Now here it is a rational function. That means it is a function of the form p by px upon qx. And the limit is asking at x is equals to 0. So at x is equals to 0, the q of 0, which is nothing but 0 plus 1, is equals to 1, not equals to 0. And we know that whenever we have a rational function in which denominator is not vanishing at 0, it will be continuous, right? So the limit was nothing but just substitute 0 in place of x. You will get -1. Okay. So it's an easy example. Now let's try to answer this question. So find the limit x goes to infinity of 1 plus x cube upon 1 minus x to the power 7.
0.
Yeah, sure? Yeah, its answer is 0 though. Again, whenever you have such kind of function where the much higher value of x involves, and we know that as x goes to infinity, this x cube will also go to infinity, x to the power 7 also goes to minus infinity. So here we are getting some infinity by infinity kind of case, right? So whenever we have such kind of thing, we try to reduce in terms of lower power of x or 1 by x type of thing. So here what we do, we just take out common the highest power of x. So limit x goes to infinity will be there. Here I'll take common x cube. So it will be 1 by x cube plus 1. And the denominator I have x to the power 7. So it will be 1 by x to the power 7 minus 1. Right. So here this will be equal to limit x going to infinity of 1 by x to the power 4. And then here I have 1 by x cube plus 1. And here I have 1 by x to the power 7 plus 1. So ultimately what I did, I decompose my expression into such kind of function uh, about which I know the limits, right? I know that limit x going to infinity, 1 by x to the power 4 is equals to 0, right? And similar kind of thing with this. So that means as x goes to infinity, this goes to 0, this goes to 1, this goes to 1. So ultimately what I have, 0 into 1 by 1, which is equal to 0. So that's why the answer is 0. Is that fine? Any doubt in this question? Anything you want to comment? No? Okay. Now I'll give you one question here. So suppose f of x is equals to x square plus 4x plus 3, when our x is less than or equal to 0, and it is some x plus m when our x is strictly greater than 0. Suppose f is continuous and this function is continuous, then you have to find out the value of m. Find the value of m. Again, answer in the chat box, that will be helpful. Okay. I don't think it's that tough, but yeah, try to solve it.
Three.
Yeah, correct. What about others? Correct. The answer is 3 because it's quite easy. Since the function is continuous at x is equals to 0, we have a left hand limit of f at x is equals to 0. So whenever you see such kind of question, you have to use this concept, that the left hand limit of f at x is equals to 0 is equals to right hand limit of f at x is equals to 0, and it is equals to the function value f of 0. Okay, so here what is the left hand limit of f at x is equals to 0? So from the left hand side of 0, we are actually following a parabola, right? And we know that parabolas are continuous. So the left hand limit is nothing but just put x is equals to 0 over this parabola. So I'll get 0 square plus 4 into 0 plus 3, which is equals to 3, right? Now what is right hand limit of x at x is equals to 0? So from the right hand side, the function is actually following a line. And we know that the line is also continuous. So the limit is nothing but the value at x is equals to 0. So it is same as 0 plus m. So it does not actually require this particular thing, but although you can compute using these two also. So ultimately what I'll get m is equals to 3. Okay, that's our value. Is that fine?
Yes, ma'am.
Okay, so I just have these all questions. If you guys have anything in your mind, you can ask now, or else we go to that particular discussion. Someone says he has some plot over epsilon and all things, right? So we can discuss that. Any topic from week 3, week 4 you guys want to recall, or something else you can say, because that's all from my side. I just have these many questions and that revision only. Anyone?
Ma'am, if a sequence is bounded above and below, then can we find the exact bounded value?
Exact bound?
Yes, can we find any like number, say that's the bound of that sequence?
Yeah, so that those two particular numbers are known to be supremum and infimum of that particular sequence. So that means what happens, so suppose you have a sequence an which is bounded above and below, right, which is bounded above and below both. So then actually you can find out two numbers. They are known to be the supremum and infimum of this particular sequence an, which has this property. So a supremum of a sequence is nothing but a number in such a way that it possesses two properties. So first thing is that all an is less than equal to its supremum, so that means it will be an upper bound. And the second thing is it is the infimum of the all its upper bound. So that means if you just if you take any what do I mean by that? So if you just take any number and subtract it from an, so again let epsilon strictly greater than 0, then an minus 0 if you take, then there will always exist a term which is less than or equal to this term, this number, and which is greater than or equal to the supreme. So ultimatum meaning is the supremum is something like this, that if you just go a little below of this line, you will find a sequential term which is actually greater than this particular line. This is your an minus epsilon. Sorry, here I written in wrong way. There will always exist supremum minus epsilon is greater than equal to a. That means if you just go a little below of the supremum, you will always find a limit, always find a value of function where this thing can happen. That particular is known to be a supreme. That's why I say that upper bound is not unique, but these an infimum is same as for lower bound. So that means if you go just a little above from the infimum, you will find out a term of sequence which is lesser than that. Okay, so this is known to be supremum infimum of a sequence. So yeah, upper bound and lower bound are not unique, but a supremum and infimum of any sequence is unique. Is that fine for you?
Yes, ma'am.
Yeah, so such kind of thing I think you guys will learn in mathematical thinking course. If you take there, they describe these all things. It's a degree level course. So if someone is really interested in maths, I mean the theorems, the proof and all, then he or she can take. Okay. Anything else you guys want to discuss? Yeah, someone says that he has some plot over epsilon value and the value of function. Any doubt if you guys have, you can ask now from week 3, week 4, or any concept you want to recall. And I'll upload this notes over the calendar as we usually do.
Ma'am, I have doubt in big 3.3 activity question 1.
3.3, question number 1.
Yeah.
Okay. So what's your doubt here? You have to find out the nth term of a sequence of the series, sorry, not the sequence. So this is your doubt, right? This question?
Yes, ma'am.
Yeah. So here what you have to do, you want to find out the value of en. Un, right? So here observe the first term. So the first term is 1 square upon 2 square, right? The second term is 1 square into 3 square upon 2 square into 4 square. So what is happening here? So if I take, so that means here 3 can be written as 2 plus 1, or it's an the next odd number, right? Here 1 is there, 3 is there, then 1, 3, 5 is there. So that means here it is coming to be the next odd number. Next odd number, right? So if so you know that odd numbers can be written in the form of 2n minus 1. So if you consider this expression, you can actually construct all the odd numbers from starting from 1, because if I take n is equals to 0, if I take n is but here n is ranging from 1. So if n is ranging from 1, but yeah, n is equals to 1 is also fine. So if I take n is equals to 1, n is equals to 1 if I'll take, but I'll get 2n minus 1 will be equal to, then 2n minus 1 will be equal to 2 minus 1, which will be equal to 1. N is equals to 2 will imply 2n minus 1 will be equal to 3. So that means 2n minus 1 is the expression which actually saying that this will be an odd number, right? So if un is there, then obviously in the numerator we have 1 square into 3 square into 5 square into and so on. So the nth odd number is given by 2n minus 1. So it will be 2n minus 1 whole square. So numerator we figure it out. Now what about denominator? So denominator in the denominator also the thing is happening that it's the next even number. Now you have to figure out what will be the nth even number can happen, right? So the n is equals to 1, we have here 2 square. N is equals to 2, we have here 2 square into 4 square. N is equals to 3, we are having actually 2 square into 4 square into 6 square. So if I take in place of n, if I take 2n, okay, so if I take 2n, then but here in the option when n square is there, n square won't work. 2n we can take. Yeah, 2n is there, right? Then the first option 2n is there. So if I take 2n to be my the nth term, so then if n is equals to 1, this 2n will be equal to 2, right? N is equals to 2, this 2n will be equal to 4. N is equals to 3, this 2n will be equals to 6. That means this 2n is actually giving me the recursive even numbers, the next even numbers, right? So that means here the denominator will be 2 square, 3 square, 2 square, 4 square, 6 square, and so on, 2n the whole square. So the option number 1 is the correct answer. Okay, is that fine? You have to judge
Yes,
what will be your un.
sir, but my doubt is un is simply 2n minus 1 whole square divided by 2n square. Then why we multiply it
No,
1
no, no,
square,
no.
3 square, 5 square?
No, here observe that this sum is different, but this is your un. So your your u2 is actually 1 into 1 square into 3 square upon 2 square into 4 square, and your u3 is this whole term. The term is there, right? I mean, the whole term is there. So every term is actually taking multiple and then adding. So here your u2 is 1 square into 3 square upon 2 square into 4 square. Your u3 will be, the whole term will be there. That means 1 square into 3 square will be there. 2 square into 4 square will be there. And then multiplication of 5 square into 6 square. That's why we are taking this whole multiplication. Okay.
Yes,
Fine.
ma'am. But when we put n equal to 1 in first equation, we didn't get
Mhm.
1 square by 2 square only. It's a long term, ma'am.
No. So then, see, if you take n is equals to 1, then you are not taking a 1 square upon 2 square and all thing. So here it's a recursion thing. So if you take, if n is equals to 1, then it's simply one term only. So un is equals to only 1 square upon 2 square. So that means here the number of term is also different. So here if un is, see, if you, in the u2, see, in the u2 there are two terms in the numerator, right? In u3 there are three terms. So in the un there will be n terms. So this is the first term, second term, fourth term, and so on. So in the u1 there will be one term only. So in the u1 there will be one term only, and that one term is 1 square by 2 square. Okay, got it? What I want to say?
Okay, ma'am.
That means
Got it.
here the
Got it.
number of term is, the term is also increasing. Okay. Anything else you guys want to discuss?
Ma'am, in before lecture, professor taught us about something nth root of any function. Find nth root of any function from limit.
Yeah.
In some lecture, I didn't get that too much. Can you explain it?
Yeah, actually, see, as we nth root of something, right? See, we have one sequence which actually converges to root 2, right? We have a sequence which converges to under the root of 2, right? I don't have that sequence now. Yeah, so this is the sequence. So similarly, I mean, we have one sequence which actually converges to root 2. So similarly, we can find a sequence which converges to root d, where d is any natural number. And that sequence is given by, so here un plus 1 is equals to 1 minus 1 by d of un plus a by, sorry, this will be 2 and this will be d by 2 times un of Sn minus 1. Okay, so if you consider this particular sequence, this sequence un, so then it actually takes a little bit effort to prove that the sequence is convergent. First, we will show that this sequence is bounded and bounded, and I mean, there is a particular method for finding out that this sequence is convergent. There will be two subsequence and all those things, but ultimately what happened, this sequence will converge, and what will be the limit of this sequence? So the limit of un is nothing but the under the root of d. So that's the thing, sir told, that for any root, for any nth root, we can find a sequence which actually converges to that particular root. And here I am taking 1 by 2, you can take any number, 1 by s is also fine. So the one line purpose is that you can find out a sequence which can converge to root n. But yeah, for saying that this sequence is convergent and all, it take a little bit effort. So you can find it in some books. Is that fine for you? Ritu, I guess.
Okay, ma'am. I will find it from anywhere else.
Because the proof involves subsequence and their limit concept. So I don't think you guys are familiar with that. So you can find it in the Rudin book. wrote in for mathematical analysis. I think it contains proof. Okay, so if you guys don't have anything, we can wind our session here. Or any doubt if you have from week 3 and week 4, you can ask. Any concept which is not clear, you can ask, because the exam is very near now. You can't spend more time on just grabbing the concept now, right? You have to focus on your practice, the application part. Anything from anyone?
Can you please explain a little bit of monotonic conversion?
MCT?
Yes.
Yeah. So monotone convergence theorem actually take two property of a sequence and combine them and tell us that a sequence is convergent or not. Okay. So the statement is uses two things. So first thing is, if you have an increasing sequence which is bounded above, then it will imply it is convergent. So why this actually happen is, if you consider the plot of a sequence, so suppose here I'll plot sequence. So the term of what does monotone convergence theorem means? So it says that first thing is it is an increasing sequence and the second is bounded above. So bounded above means I am able to find out a one number, capital M, in such a way that any term of a sequence cannot cross this particular ceiling by this capital M, right? This is the meaning of bounded above. Bounded above means all the terms should be less than or equal to this capital M. Now, why I'm taking here increasing also? Because if you plot your sequence, then there will be some time where the sequence increases, right? Increasing matlab, if this is an, so this is an plus 1. So then an plus 1 should be greater than or equal to a. This case should happen. Then only it's an increasing sequence. So if it is an increasing sequence, then it slowly, goes up. And because of the increasing nature, it cannot go down. It always either it can grow up or it can stay constant, right? So when we combine these two property, we actually get one thing. We get one strip here, one L, over which the infinitely many number of sequence will converge. So that's why it is a convergent sequence. So that's happened in the graphical way. You can understand, since there is a one ceiling here, the one bound, so it cannot cross this particular capital N. And since it's an increasing sequence, it cannot go down. It always either go up or stay constant. So if it stay constant, we get our limit. Or also if it grows up, then it cannot go above than this particular M. Then our M will be limit. Okay, so this is the main thing happen in monotone convergence theorem. Now, the application of monotone convergence theorem means they will give you some sequence, and there you just have to find out these two property. It is increasing, decreasing or not. And mainly monotone convergence theorem are usable when we have recursion. When we have recursion type of sequence, recurrence sequences. There it is much applicable. I don't have a good example now, but if you have any example in mind, we can solve it to see how we are applying monotone convergence theorem.
I don't have any examples.
Okay, yeah, so this 3n plus 2 upon that example is okay. It is also decreasing, or else let's try this one. Let's try this example. So its example is an plus 1 is equals to 3n plus 2 upon, if I take anything upon, then I don't know what happened. Okay, so see. So an plus 1 is equals to 2n square minus of 12. Let's take this one with a1 is equals to 0. Okay, so if you consider this sequence, then obviously it's a recursive sequence. So is it bounded above? Sorry, first thing is increasing or decreasing. So is it increasing or decreasing sequence? Can you guess? See,
Increasing one.
increasing sequence. So in such kind of sequence, what you can do, you can try to figure out the what you can say sign of an into an minus 1. So here if I do an plus 1 minus an, then it is same as 2an square minus an minus 12. So if this is a quadratic equation. So if I try to find out the root, so the root will be a little bit difficult in this case. So let's take it to be 1 only. So 1 an square upon, okay. So then the root will be, we want multiplication to be 12 and addition and summation to be minus 1. So here minus 4 into 3 works, right? Minus 4 plus 3 will be minus 1, multiplication will be 12. So here it will be an minus 4 into an plus 3, right? So now a1 is equals to 0 is given to us. A2 if I compute, so it's minus 12. A3 if I compute, then it is minus 12 square minus 12 and again a positive quantity. So that means ultimately an is greater than equal to 0. And we also know that an will always come above this minus 4 also, because this is A3 is 12 square minus 4. That means 144 minus 12. So it is nothing but 132, right? And it is strictly greater than 4. Again, if you compute A4, so it will be 132 square minus 12, again greater than 4. So that means an is greater than 4, an is greater than 3 eventually. So what is happening? An plus 1 minus an is greater than equal to 0. So that means it's an increasing sequence. So now what about bounded above or bounded below property? What you can say? It is actually not bounded above. So it is not bounded above. Why it is not bounded above? Because here if you guess by the term, we are actually growing very faster and faster. That means A1 is 0, A2 is minus 12, which is less than 0, but A3 is 132, which is more far away from A2. And A4 is again a big quantity. So that's why it's not bounded below. So that means it is not convergent sequence. Convergent sequence. So it is not that good example of MCT, but yeah. How to find one example for MCT. Increasing and bounded above. Okay, see. Anything else you have? Because I actually don't have any examples for this one. Any doubt in this particular example? This one?
No, ma'am.
No, right? It's pretty
Excuse me,
straightforward.
ma'am.
Yeah.
Can you go little down? Ma'am, up. Stop there.
Mhm.
Ma'am, what if you just put A1, A0 equal to 12? Can you just go down little more? There.
Mhm.
Can you just put A1 equal to 0 and put N equal to 0 and then find A0 equal to 12, okay? A0 square equal to 12.
A0 square equal to 12, okay.
Are you getting that?
No, actually, what do you mean? You want
I
to
mean
change the
that
sequence?
if I will find A1 equal to 0 and put that equal to 0, like
A1.
an plus 1.
Mm-hmm. So it is 0
So
minus 12, it is minus 12.
not minus 12, 12.
Minus 12.
No, just 12, no, positive 12.
Why positive 12?
Because I'm putting n equal to 0 so that I will get a1 and then put an square minus 12 equal to 0.
Okay. Sorry. So that means you say that start with a naught. A naught is 0 for you, right? This is the
Okay.
a naught is equals to 0. So then your a1 is equals to 0 square minus 12. That will be minus 12. Then your a2 will be minus 12 square minus 12. So yeah, this will be 132.
Then
So,
if I know that a0 is positive and the function is quadratic, so can't I directly say that it will be an increasing function?
yeah, you can directly say also that it is an increasing function. But see, it is not explicitly quadratic. I mean, explicitly quadratic means if I give you a sequence instead of this, if I say an is equals to 4n square plus 5n plus 7, right? Now this is explicitly quadratic, but here an is involved, right? So it actually depends on the nature of this particular
But I
an.
found out now that an is a positive number, and then I can put that an is a positive
After
number.
computing these three terms, you can say that okay, it is a quadratic expression. It will blows up. So yeah, it is an increasing and amount. Yeah.
But let me clear that one thing. What if I don't find three numbers? I just find a0 equal to 4 root 3. That is 2 root 3. And if a0 is positive, then the quadratic must be positive, I think.
If a0 is positive, then the quadratic will be positive. Yeah. Correct. Now I get. You mean that since this power is 2, so no matter whatever I'll take, it will again blows up, right?
Yeah, exactly.
Because if here I'm getting minus 12, it does not matter what I get. Ultimately, it will give us a very large quantity because of this
Positive.
2, right?
Yeah.
Yeah, you are correct. You can also judge by this.
Okay, thank you.
Because again, we are squaring, so the number will large. Okay.
But
Anything
ma'am,
else?
excuse me, ma'am. As he said that it will be 0 and minus 2 and plus numbers. So, as you said before, it should be an increasing sequence, right?
Right, but
So,
only 2 numbers does not matter that much. 2 or finite
okay.
number for us.
Okay.
Initially, if you get 2 or 3 number which is not showing you increasing decreasing behavior, it actually does not matter in the sequence because we have infinitely many terms. We just start our sequence after this. Although it does not happen in the exam that you will find such kind of thing, we eventually
No, ma'am,
give you
I'm
either
just
increasing
clearing
or
my doubts. That's it.
yeah. Okay, so let's end our session here, I think. Or else if you guys have any doubt, you can still ask. I'll be here for 10 minutes. But if you don't have, you guys can leave and see you in next session. All the best for you.